Okay, in the last segment, we introduced the idea of the boundary layer and the fact that fluid mechanics is very important in terms of determining the convective heat transfer coefficient. What we're now going to do, we're going to look at the flat plate again, but we're going to consider only the first part of the flat plate boundary layer flow, and that is where we have a laminar boundary layer. So in analyzing the laminar boundary layer, some of the earliest development came with Ludwig Prandtl, and what he did is he took the Navier-Stokes equations, and these are the governing equations for fluid mechanics, basically F equals ma. And he took the Navier-Stokes equations and he simplified them for a boundary layer flow. And then what happened is one of Prandtl's students, Blasius, he solved these equations through numerical hand calculation. And so the Blasius solution is what will become the basis of a lot of the results that we're going to be using when we look at the laminar boundary layer. One thing that I should say is that no exact closed form analytical solution exists. Blasius solution only comes about by doing numerical integration, and consequently you get a table of values that you can use for the velocity. Now, Theodor von Karman a little later played around with different types of profiles, quadratic, cubic, and he came up with approximations for the velocity profile, but it was not an exact velocity profile like Blasius's came out to be. And both von Karman and Blasius were students of Prandtl at Göttingen in Germany. And so what von Karman came up with was a velocity profile that looks something like this. You divide by the free stream, and this is looking at a quadratic. There's also cubics that he came up with, different functional profiles. And so if you want, you can look at my fluid mechanics lectures, and I go through the use of this profile for coming up with things like the skin friction coefficient and the momentum thickness. We're not going to worry about that now in this lecture because we're looking at heat transfer. But looking at the velocity profile, it would be something like this. Here's our flat plate. Remember, x is going in the direction of the flow. Y, when we're looking at boundary layers, is always normal to the plate. And then we have our delta of x and our velocity profile. And so here is the velocity profile. Once we get out into the free stream, we get to u infinity. And here we have u, and I'll show it of, sorry, not y, it's u. The velocity u of y, and really implicitly it's also of x. And that results, given the fact that delta of x is in here, and consequently it is scaling with u, with y and x. And delta, the boundary layer thickness, is delta of x. And remember, we said that's where we get the 99% the free stream. Now, that is a velocity profile that von Karman came up with. Now, with Blasius, he was able to, using his numerical integration, come up with the value for delta of x. So let's take a look at what that value was obtained as being. And he got delta of x, the boundary layer thickness was 5.0x divided by Reynolds number of x to the 1/2. And so this was Blasius solution. Okay, so that is only 1/2 of the problem, and I'm not going to go through and come up with a Blasius profile. You can look in textbooks of fluid mechanics and find that some heat transfer books may have it as well. But having the velocity profile is only 1/2 of the problem, because really, remember, we're interested in heat transfer and the convective heat transfer coefficient. So we have to go a little bit further than that. Okay, so having the velocity profile, that's only taking us halfway. What we need to do, we need to determine the convective heat transfer coefficient. And so how can we go about doing that? Well, it turns out that you need to be able to get the temperature profile in the boundary layer in order to estimate the convective heat transfer coefficient. And let's take a look at how we may go about doing that. So here we have the flat plate again. I assume that's our boundary layer. And here we're assuming that the flat plate, oops, not T infinity, that should be T wall. And then we have some flow field. And this is not the velocity boundary layer that I'm drawing. This would be a profile of the temperature distribution. Let's say the wall is hotter than the fluid. You may have something that looks like that. So that would be your temperature profile. And then eventually you get to the point where you are at T infinity, which is the free stream temperature profile. And what we're going to do, we're going to introduce a thermal boundary layer thickness, which is going to be a function of x as well. And so that would be the point where we get out to the free stream temperature, and you do not see the presence of the wall any longer. So T of y, remember y was normal to the wall. And the result of this is we have heat transfer taking place, and so there's Q. And we know through Newton's law of cooling we have the convective heat transfer coefficient, which is what we're ultimately after here. So looking at the equations, what we can do, we know through Fourier's law and what I'm doing is I'm taking advantage of a thing called the no-slip boundary condition. And what that means is right along the wall, if we look at the velocity profile, that's not a very good plate. Let me do this. Okay, so here is our flat plate. And if we look at the velocity profile right along the wall, if you were to go microscopically into the wall, at the wall, the velocity is 0. U at y equals 0 is equal to 0. And so that is what we call the no-split boundary condition. And with that, the only mechanism of heat transfer when there's zero velocity is going to be via conduction. And consequently, we can use Fourier's law. And so that's what we're doing with this expression up here. And we also know that through Newton's law of cooling, is going to be equal to H times T wall minus T free stream. And we have that expression. So what I'm now going to do is I'm going to work to isolate H. So let's isolate H. And we obtain that expression there. And so this is going to be the basis by which we're able to determine the convective heat transfer coefficient for the laminar boundary layer flow that we're looking at. But in order to get this, what we need to do, we need to know temperature as a function of y. And that is part of the solution technique that is required. So we need to know the temperature profile. Okay, so in order to get the convective heat transfer coefficient, we need to know the temperature profile. And then once we obtain H, what we do typically in fluid mechanics is we embed that within a non-dimensional number, and that number is the Nusselt number. So there is the Nusselt number. What it is, it's the convective heat transfer coefficient times some characteristic length scale, in this case x, the distance from the start of the plate, divided by the thermal conductivity of the fluid. And so let me write those out. Okay, so a Nusselt number is the number that we will use quite often. And one thing I should say is notice we have Nusselt number X, that denotes that this is a local Nusselt number, not an average. Other times you'll see Nusselt number with an over bar. That denotes average for an entire plate. So just be careful. This Nusselt number refers to convective heat transfer coefficient evaluated at some specific X location. Other times this would have H bar, and that would be the average convective heat transfer coefficient over an entire object. But anyways, that is the Nusselt number, and that is what we will use, just like the Reynolds number, but we'll use it for characterizing the amount of convective heat transfer coefficient on some object that we're studying. So that's the laminar boundary layer, the Nusselt number, and what we're after, we need to get the temperature profile. So what we are going to do in the next segment, we're going to take a look at the thermal boundary layer in relation to the viscous boundary layer, the velocity boundary layer, and they are related to one another, but we'll be looking at that as we move along, looking at an introduction to convective heat transfer.